Hello, everyone. Today, I will talk about dynamic inference in probabilistic graphical models. This is joint work with Weiming, Xiaoming, and Yitong. At first, let me define the graphical model. Given a graph, V is the set of vertices, and E is the set of edges. Suppose each vertex is a random variable that takes its value from the finite domain Q. And suppose each edge is a constraint defined on its variables. For each variable v, we give it a weight function phi. The function maps the assignment of v to a real number. For each constraint e, we give it a weight function phi. The function maps the assignments of all variables in this constraint to a real number. Now, for each configuration sigma in Q to the V, where a configuration is an assignment of all random variables, the weight of sigma is e to the sum of all the rate functions power. Now we can use variables, constraints, domain, and weight functions to specify a graphical model. The graphical model defines a Gibbs distribution mu such that the probability of each configuration is proportional to its weight. Here is an example of graphical model. Given a graph Z, a proper Q-coloring of Z is a coloring of the vertices with colors from 1 to Q such that any two vertices of an edge have different colors. For example, the left picture gives a proper 3 coloring, while the right one is not a proper coloring. The proper Q-coloring model defines the uniform distribution mu over all proper Q-colorings of Z. One can verify that this is a class of graphical models, because if the weight functions are set as this formula, then the Gibbs distribution of the graphical model is exact the uniform distribution mu. The graphical model is very important in many research areas. One of the most important computational tasks for graphical model is to estimate the distribution of a vector of random variables. This problem is very motivated and also well studied. Given a graphical model instance, there are three kinds of probabilistic inference problem, including the marginal inference, the posterior inference, and the maximum posterior inference. There are different methods for probabilistic inference. In all these methods, MCMC sampling is the most widely applicable. Given a graphical model I, the sampling algorithm draws random samples from its Gibbs distribution. Thus, given n independent samples x from mu I such that the total wireless distance between x and mu I is bounded by epsilon I, one can estimate the target probabilities that I from these samples. The needed number of samples Ni depends on the instance I and the desired quality of estimate. Similar for the area of each sample. Usually, the target probabilities are simply estimated by counting the frequency of the samples that satisfy certain properties. Nowadays, the big data proposes new challenges for the inference methods. The graphic models from big data usually have huge size. Moreover, these models are updated frequently, though the difference between the models before and after an update is usually small. For these models, running the whole inference algorithm for each update is too time cost. For example, if the MCMC sampling is used, for each update, the running time is big omega of the product of Ni and the size of V. However, the size of V can be as large as several billions, and Ni can be as large as several millions. Another example is the practical algorithms for learning graphical models, such as the constructive divergence algorithm for learning the restricted Boltzmann machine. In these algorithms, the optimal model I star is obtained by updating the parameters of the graphical models iteratively, which generates a sequence of graphical models with the goal that the final graphical model is a good approximation of I star. To obtain the next graphical model, the gradient is calculated by performing the probabilistic inference in the current graphical model. In these algorithms, run the full inference algorithm for each update is 2 time cost. Thus, in this paper, we consider the dynamic inference problem. Given a graphical model I, let I be the target probability vector, and let hat I be its estimator. In dynamic inference, we all know the graphical model itself can change dynamically with time. Specifically, we can add and delete the variables and constraints and change the weight functions. The goal is to estimate the target probability vector that I prime. The main question in this work is that can we modify the estimator set hat I to the new estimator that hat I prime with small incremental cost such that hat I prime is a reasonable estimator? The dynamic inference problem is formulated in this yellow box. The input is the original instance I, the original estimator that hat I, and the update instance I prime. The output should be a new estimator of the updated graphical model. To accelerate the inference algorithm, the extra data structure resided in the memory is allowed. Once the instance is updated, the data structure should also be updated. In this talk, we'll show all the updates are generated by an offline adversary. The update is independent with the randomness used by the algorithm. Moreover, we've also shown that the difference between I and I prime is bounded. Otherwise, there is no faster dynamic algorithm than static inference. Here, the difference between the instances is defined as this formula, which is the sum of the symmetric difference of the vertex set, the symmetric difference of the edge set, and the one norm of the difference between the weight functions. The main contribution of this work is a new algorithm that solves dynamic inference problem efficiently. For a broad class of graph models, our algorithm is fast. We prove that if the two instances have a polylogarithmic bounded maximum degree and satisfy the Dobrich-Shalotsman condition, the expected running time is bounded by the sum of Ni prime and the size of V prime. Actually, for most such instances, the only applicable static inference algorithm is MCMC sampling. Thus, the expected running time is no less than the product of Ni prime and the size of V prime. Therefore, our dynamic algorithm achieves a significant speedup. Our dynamic inference algorithm is based on dynamic sampling. The extra data structure stores the samples from the current instance. Once the instance is updated, the inference algorithm first updates the samples and then updates the estimator based on these samples. Thus, to solve the dynamic inference problem, we first solve the dynamic sampling problem. Suppose we have a graphical model I, and we also have a random sample X that follows precisely the Gibbs distribution from this graphical model. Let I prime be the updated instance. The main question is that can we modify the sample x to a new sample x prime with small incremental cost such that x prime follows precisely the Gibbs distribution of the updated graphical model. This problem was partially solved by dynamic rejection sampling. The algorithm is vast but limited to soft constraint and one-set update. In this paper, we propose a new algorithm, namely the dynamic Gibbs sampling. The algorithm maintains an extra data structure for the Markov chain of the current instance. Once the instance is updated, the data structure is also updated. Comparing to the dynamic rejection sampling, our new algorithm is more flexible. It's applicable to hard constraint and universal update of the weight functions. Moreover, it achieves almost the same regions as static sampling for typical graphical models. The main idea of dynamic Gibbs sampling is constructing the chain on I prime by modifying the chain on I slightly and efficiently. We define a coupling of the chains xt and yt, where t is from 0 to infinity, such that xt and yt are similar and then yt can be obtained by modifying xt slightly. We use efficient dynamic data structure to store the Markov chain such that the modification can be realized efficiently. Concretely, given the chains xt on I and yt on I prime, if I and I prime are similar, then we can initialize the chains with similar initial states x0 and y0. Because x0 and y0 are similar, the chains can be updated with similar delta x0 and delta y0. Thus, x1 and y1 are also similar. Iteratively, we have all xi and yi are similar and delta xi and delta yi are also similar. Thus, yi can be obtained by modifying xi slightly and delta yi can be obtained by modifying delta xi slightly. Overall, our dynamic inference algorithm includes 3 steps. Firstly, we perform the dynamic Gibbs sampling algorithm to obtain n-high samples such that the total variance distance is no more than epsilon high. Secondly, we adjust the number of samples and the area of each sample. At last, we calculate the new estimator based on these samples. The dynamic Gibbs sampling consists of 4 subroutines. The first one is the subroutine for weight function update. The second one is the subroutine for adding variables. The third one is the subroutine for constraint update, and the last one is the subroutine for deleting variables. The subroutines for weight function update and constraint update are the most technical. In the following, let's concrete on the subroutine for constraint update. Firstly, let me explain what is the Gibbs sampling at first. Given an instance I, let gamma vi denote the neighbors of v in the graph of I. For each edge uv in E, let buv denote the set of all possible configurations of gamma vi that differ only at u. One can verify that the marginal distribution of mu I on V conditional on sigma is as this formula, and the distribution can be calculated based on the local information of V and gamma Vi. Define the influence matrix of this formula. The Dobrich-Shalotsman condition requires that the maximum sum of the rows of the influence matrix is bounded by 1 minus delta, where delta is a positive constant. The Gibbs sampling algorithm is performed as follows. At the beginning, pick an initial state arbitrarily. In the following, for each step, pick a vertex Vt from V uniformly at random. The value of this vertex is drawn from the marginal distribution mu Vti conditional on the current assignments of gamma Vti. For other vertices, the values are unchanged. The mix time of a Markov chain is the number of steps needed to achieve a given total variance distance. Though the Gibbs sampling is simple, it can be proved that if the instance satisfies the Dover-Shalotsman condition, then the chain of Gibbs sampling is fast mixing. Thus, it's easy to obtain the following observation. The Markov chain of Gibbs sampling can be recovered from x0 and the execution log, which only records Vt and xt for each step. Therefore, the dynamic Gibbs sampling for constraint update can be realized by updating the initial state and the execution log of the current instance to that of the new instance. Note that the mixing time of the current instance may be different from that of the new instance. Thus, the dynamic Gibbs sampling algorithm first updates the value of Vt in each step, and then adjusts the length of the execution log. The value update subroutine is the core of the algorithm. In the following, let me explain this subroutine. A tool used is the coupling of distributions. Given two distributions mu and nu over omega, the coupling of mu and nu is a joint distribution of x and y, such that the marginal distribution of x is mu and the marginal distribution of y is mu. The optimal coupling of mu and nu is the coupling that attains the maximal probability of that x and y are equal. Thus, given two instances that only the constraints are different, one can define a coupling of the chains of Gibbs sampling on these two instances. Let xt, where t is from 0 to infinity, be the chain on I, and yt be the chain on I prime. Initially, x0 and y0 are equal. In the following, for each step, pick a vertex Vt from V uniformly at random. The value of all other vertices are unchanged. Where xt Vt and yt Vt are assigned according to two different cases. If gamma Vti and gamma Vti prime are equal, then xt-Vt and yt-Vt are sampled from the optimal coupling of these two marginal distributions. Otherwise, they are sampled from the marginal distributions independently. Actually, the pseudocode in the red box defines a coupling between the conditional marginal distributions. Thus, the pseudocode in the yellow box is exactly a coupling between the chains. Given the chain xt and the picked vertices Vt, where t is from 0 to infinity, we can recover the chain Yt according to the coupling. Initially, set y0 as equal to x0. In the following, for each step, set all the values of the vertices other than Vt as unchanged, where yt-Vt is assigned according to two different cases. If gamma Vti and gamma Vti prime are equal, then yt-Vt is sampled conditioning on xt-Vt according to the optimal coupling of these two marginal distributions. Otherwise, it is sampled from the marginal distribution. Because the chain Yt is constructed according to the coupling between xt and Yt, one can verify that if xt and Vt form a chain of Gibbs sampling on instance I, then Yt is a faithful copy of the Gibbs sampling on instance I prime. Moreover, in the constructing algorithm, one can verify that if gamma Vti and gamma Vti prime are equal, and their assignments are also equal in step t-1, then Yt is equal to xtvt. Thus, the execution log on prime can be efficiently constructed from the execution log on I. Since to obtain Ytvt, xtvt needs modifications only if gamma Vt and gamma Vti prime are different or their assignments are different. To realize the modifications efficiently, we maintain the execution log with efficient dynamic data structures. The running time of the algorithm for constraint update is shown in the formula. The first factor is the total number of modifications, and the second factor is the time cost of each modification. According to that, the difference between I and I prime is bounded. We have the first term is bounded. According to the Dobrich-Shalansman condition, we have the second term is also bounded. By employing efficient data structures, the time for each modification is also bounded. Thus, the overall time is bounded by the product of the difference between I and I prime and the down polylog function of the size of V prime. In this work, we formulate the dynamic inference problem. We give a dynamic inference algorithm based on dynamic sampling. The algorithm is fast on a broad cast of graphical models. The core of our algorithm is the efficient dynamic Gibbs sampling. Here are some future works. One open problem is to extend our method to graphical models with unbounded degree. Other open problem is to apply our method to learning RBM. Thank you.